Hey, welcome to Pre-Cal, Section 7 for Day 1. Just kidding. But I'd say 98% of 7 for Day 1 is Pre-Cal material. So this should be mostly just a review to you. So we're looking at exponential growth and exponential decay. We've got two formulas that we commonly use for these. This formula strictly is used for compound interest. So if you have an investment where your interest is compounded annually, I doubt you'll ever see that. Quarterly, maybe 4 times a year. Monthly, daily, 365 times a year. This is the formula that you use. And just a quick review of what all these things mean. P is your principal amount. This is the amount that you would deposit into your bank. R is your interest rate. Make sure you input it into your equation as a decimal, not a percent. So make sure you move that decimal over 2 places before putting it in your equation. N, both ends, 2 places, represent the number of times that interest is compounded. So if it's compounded quarterly, then N would be 4. And then T, of course, stands for the number of years that your money is going to be sitting in the bank earning interest. And then the Y, or whatever answer over here, that's your ending amount of money. When it's all said and done, how much money do you now have? And then this is for continuously compounded interest or any type of exponential growth. So when it comes to money, P is your principal amount. You know that E is a constant, 2.7-ish. Your rate goes here as a decimal. Number of years, ending amount. Much easier. This formula, the compound formula, works for more situations other than just continuously compounded interest. Any type of continuous growth, like population growth or decline. Bacteria growth, if you're looking like in a petri dish or something like that. Half-life and decay problems. Those are all continuous decay. And then, of course, some money applications. Okay, so a couple of questions when it deals with banking. We're going to deposit $800 in an account, 6.3% annual interest. So, 2 things I see about this problem. $800 isn't a huge amount of money to invest in a bank, to leave it in there for a long period of time. You know, like if your parents have money to invest, they're going to probably have a couple of thousand maybe to invest. So that's kind of a conservative amount of money. This is a very generous interest rate, I believe. You're not going to find like a savings account that gets you 6.3% interest. Most savings accounts are going to get you like 0.1 or something crazy low like that. There are other ways to invest that'll get you higher interest rates, but even then, 6.3 is a little high. Whatever, we'll go with it. So if we're going to compound continuously, I'm going to use the PERT equation. And I'm going to have 800 as my initial investment. My rate, 0.063 times 8 for 8 years. And the amount that I have written on my paper is $1324.26. $800 continuously for 8 years. What if it were quarterly? What if, same setup, how would it be different if your interest was only awarded to you quarterly? So we're going to go the other formula. 800 is the initial investment. 1 plus rate, 0.063, quarterly. That's a 4. That's a 4. And we're going for 8 years. And that amount turns out to be $1319.07. And you'll always find that the continuous compounded interest is better than the quarterly or the annual or the monthly or even the daily. Okay, let's see. I think I'll do this one first. So this says find the half-life of a radioactive substance with a decay. Okay. So if this is the decay equation, y equals y sub 0, or y naught, e to the negative kt. This is just your general PERT equation with a few specific things for this particular problem. First of all, this is exponential decay, and we know that the rate is going to be negative. This is the starting amount, this is the ending amount. So I can call, when at time 0, this represents my y amount, starting amount. Okay, so we call it y sub 0 because x is 0. So y sub 0, initial amount, ending amount. Find the half-life. So what that means is, what a half-life means is how long it takes, T. How long does it take for this substance to eat away at itself so that only half of it is left? How long does it take so that whatever amount we started with, after that many years pass, we end up with only half of the original amount? So what I'm going to do is I'm going to try to solve for t here. So the first thing I'm going to do is divide by y sub 0. Now, when you divide these two numbers, keep in mind what I just told you. Half-life is whatever amount we started with, whatever it was. Let's say it was, I don't know, making something up here, 20 grams of some substance. The half-life says when that amount of time happens, guess how much is left? 10. So if this is 20, half-life means the ending amount would be 10. Now divide these two numbers. It doesn't matter if it's 20 and 10 or 150 or 1,000 and 500. It doesn't matter. When you divide these two numbers, you're going to get a half as your value over here. And really, we're trying to solve for t here. So we're going to have to use a logarithm to let t escape from its exponent. So I'm going to go ln 1/2 equals ln e to the negative kt. And remember, your exponents in a logarithm, this is the only time you're allowed to do that. Your exponents can move down to the front. And ln e is just 1. So if I solve for t, I get t is equal to natural log of 1/2 over our rate. And I'm not really crazy about the way they wrote the rate because they put the negative in front of k. I would just rather call it k and know in my mind that it's a negative number, but whatever. So anytime you have a radioactive substance, if you know the decay rate, that's going to be a negative number. If you know the decay rate, you can do natural log of 1/2 divided by the decay rate, and bam, that gets you how many years it takes for that substance to eat away at itself so that there's only half of it left. Okay, next one. find the age. So it takes 5,700 years for a half-life. That's to cut itself in half. That's to cut itself in half. That's not what it's asking, though. It takes 5,700 years to cut itself in half. How long is it going to take for it to lose 10% of itself? We don't want it to lose all 50% of itself. How long is it going to take to lose just 10% of itself? So, in our PERT equation, we want to figure out time so that whatever amount we started with, let's say we started with 100 grams, we've only lost 10%, which means there's 90% remaining. So if we started with 100, we would want there to be a 9 over here. Well, here's the thing, though. We can't figure that out without knowing what the rate is. Now, I think what we could do is we could use this to find our rate. We know the half-life in this problem. It's 5,700 years. I can just do if t is equal to natural log of 1/2 over negative k. And hold on, I'll talk about that when I get there. I can do 5,700 equals ln 1/2 over negative k. Turns out negative k is going to be natural log of 1/2 divided by 5,700. A tiny number. How about this? So, using the relationship that I found in the last problem, I subbed in the half-life in this problem, and I don't like the fact that they called that a negative. So I know that when I take natural log of 1/2 and I divide it by 5,700, I get a negative value, okay? And so I get a negative value. This negative value is our actual decay rate. And it's yucky. It is a terribly yucky decimal. I'm just going to leave it like this. So I'm also going to label that as R for this problem. So I can say Y equals PE, and then R is ln 1/2 over 5,700 times T. And T's still up there. T's still in my exponent. How long does it take for whatever we started with to now decrease by 10% so that there's only 90% of it left? So I can go, if you need me to plug in numbers, I'll plug in numbers. How about we start with 100, and then that means there's only 90 grams left. .9. Boy, that's yucky. natural log multiply both sides by the reciprocal. Time ends up being about 866.418 years. Seems like a long time, but when you look back at the problem relative to a half-life of 5,700 years, holy moly, it takes 5,700 years for it to eat itself down to only 50%. It only took 866 years to eat 10% of itself away. All right, I'm going to throw in just a tad bit of calculus right here. Remember I said this is about 98% pre-cal, which it is. Little bit of calculus. And I showed you this a couple days ago. If you've got a PERT equation, the derivative of y with respect to t, y prime, whatever, is same constant, e to the messy, times the derivative of the messy. And I think you'll remember how I talked about the fact that this is your original y, and look how your original y is in your derivative. So your derivative consists of the original function multiplied by a constant. Since my derivative is almost entirely equal to the original, the only difference is my derivative, it has a constant times the original. I can say that, oh dang, I can say that my derivative is proportional to my original. You know what proportional means? It's being multiplied by a constant. That's all it means. My derivative is proportional to my original. Same thing is represented over here. Watch. My derivative equals some constant times my original. My derivative is proportional to my original. My rate of change is proportional to the original equation, or the amount. My rate of change is proportional to the amount. So if this were like, well, the best way to say it is if it were population. If this were population, I could say the rate of growth of population is proportional to the actual population. So anytime you hear that phrase, that your rate is proportional to the original, or your rate of change is proportional to the amount, that's a clue you're dealing with a PERT equation. When you hear that, think PERT. So here we go. You're going to hear that. Ready? Population is growing at a rate, derivative, proportional to the original. Growing at a rate proportional to the original. think PERT. So I'm going to write PERT. Now, let's see what we can plug in there. The population was 10. Okay, so the starting population was 10. The ending population was 50. The time was 30 days. Let's plug that information in. The beginning was 10. The ending was 50. Time was 30 days. Taking that bit of information, I'm assuming I want to find the rate. I don't know. Let's see what else it says. If the growth continues, okay. So basically it's saying at the same rate, then let's answer this question. So yeah, we do need to find R first. Let's find R first. So I'm going to divide both sides by 10. I'm going to natural log both sides. I'm assuming that's going to be a very yucky decimal, so I'll just leave it like that. ln 5 over 30. Okay, what else does it ask? So at that rate, how many days after May 1st? Now remember on May 1st there were 10. How many days time will the population reach 100? Oh, all right. So if we start with 10, how long will it take to get to 100? So use the same rate that we just found. And t is what we're solving for. Multiply by the reciprocal. And I got 43 days. And again, that was all pre-cal. The only thing calculus that we used there was knowing that the rate of change was proportional to the original population equation, and that clued us in that it was a PERT equation.